Okay. Hello, Orsolya. Hi.
Yeah, good evening.
Morning. Nice to meet you. Welcome. Would you like to try your presentation firstly?
Yes, just give me 1 sec. Okay. Do you see my screen?
Yes. Good.
Great. And you are still seeing my screen, right?
Yes, everything fine.
But and you see.
I see your title, your topic, structures and patterns.
Okay, but and you see the regular view and not the transcript.
Yeah, the regular one.
Perfect.
Yeah. Thank you. So I would like to firstly give you a brief introduction and followed by your lecture. And I think we can have a break in the middle of the lecture and then by some discussions at the end. I think around two classes. Yeah. Okay.
Great.
Yeah. Wait a moment. So some students still they are coming in. Okay. Oh, sorry, shall we start?
Yes.
Yeah.
Let's
Okay.
start.
Good morning, Orsolya and Gaspar, and good evening, all the PhD and postdoctoral students. Welcome and participate in this special courses lecture series organized by both Digital Future and Tongji University. So we have a list of prominent guests from all over the world, and will give us a lecture series, especially focus on the structural performance-based design. I think it's a super interesting topic. It's extremely, especially based on the background right now. The digital architecture is going very fast, including a lot of simulation optimization design tools is developed by different teams around the world. But still, we need to learning, especially some fundamental principles and why we should implement such softwares and design tools to solve different problems in the design process. So today, it's a great honor. We have a special guest here, Orsolya Gaspar, who is currently a visiting professor in the team of Sigrid Adrian, who is founded the lab form finding lab at Princeton University. And Orsolya is right now the Korani Fellow from 2022 to 2023. where she is contributing the project on the framework-free construction of masonry walls. She is an assistant professor at Department of Mechanics, Material and Structures, and members of Structural Sustainability and Resilience of the Built Heritage Lab at the Faculty of Architecture, BME, Budapest, Hungary. He received her PhD in historical structure in 2020 from BME for her thesis, The Role of Geometry in the Structural Behavior of Masonry Arches and Domes. In 2016, she organized the exhibition Frozen Modernity in Budapest, showcasing Hungarian reinforced concrete shell structure, and has extensively lectured on the topic since. In 2019 and 2021, she has been awarded the Hungarian National Excellence Research Grant for her study on water Bosfield works. So today, the brief introduction on her lecture is about on the background of shortage of natural resources coupled with rapid population growth and urbanization challenge. The construction industry is rethink how to build. As inspiring good practice from the near past, the lecture focuses on two chapters. From the history of reinforced concrete shell structure, shell architecture, its developments in the Hungarian before and after World War II, under constant shortage of timber and steel, and the concept of Zeiss-Dywidag system in Germany, a landmark innovation in the field of reinforced concrete structure. The latter's first manifestation was the world's first geodesic dome structure designed by Walter Bosfield, which was reportedly inspired by the lack of linear in the post-war era. So Bosfield's originally contribution to the optimization of gray shell is presented. In particular, the subdivision of spherical surface into the equal area triangles and the various geometrical metrics for the structure and ethical pre-assessment of the grid. At a short outlook connects the past with the future. A current vernacular tradition-inspired research project at the Form Finding Lab offers the new take on the framework, the formwork-free masonry constructions. So let's welcome Orsolya to give your lecture. So the screen is yours. Thank you.
Thank you very much for this introduction, and thank you for this wonderful opportunity. I'm very happy to be here. Let's dive in. So the title of my talk is Structures and Patterns. Before we start, a bit of framing. The UN says that by the year 2050, there will be 2 more billion people on Earth, which means that, bluntly speaking, we need to accommodate 1.5 million people each week. So we need to build housing for them at least. That is quite a lot, but surprisingly, given the pace of construction, is not the biggest issue. The biggest issue is that we have to do that under the depletion of our natural resources. So the challenge is that we need to keep building in a very rapid way, but we need to do it very differently than we did before. What I'm advocating in this lecture is a respectful use of materials, in specific to use the minimum amount of material that we can. There are many ways in which we can achieve that. I will cite a couple of historical examples, which I think are quite exciting from the viewpoint of innovation, because at their time, they were super innovative and they directly responded to one or multiple types of shortage. To keep things consistent, as I promised, I will focus on today on the 20th century developments of shells, but I will start with a condensed outlook on my research in masonry, arches, and vaults, as that forms the base for my current project in the form finding lab at Princeton. Then I will talk about the early history of the Zeiss-Dywidag domes. That will include also the Geodesic dome. And I propose to have a short break after that. And then when we are back from the break, I will continue with the developments in Hungary in reinforced shell architecture in the 20th century. So I have studied the mechanics of masonry vaults in relation to the geometry. The basic concept has been beautifully captured by an analogy originated from Robert Hooke, the famous 17th century English scholar who is pictured here. He said that the ideal shape of an arc is that of an inverted catenary. An inverted catenary or hanging chain is in tension. So, the hanging chain itself is in tension. So if we invert the shape, then it will be entirely in compression. And that's important because a masonry construction cannot sustain tension, only a very limited amount. And by extension, it also doesn't really work in bending. So this idea is at the core of the so-called truss line analysis of arches. The truss line, which is marked blue in this figure, is essentially the way compressive forces follow in a structure. This is kind of the generalized version of Hooke's inverted chain idea. But while the inverted chain has a catenary shape, we very rarely build arches in a catenary shape. It is not even necessary. They just have to be, the shape has to be close enough to the catenary shape. And figuratively speaking, that means that it has to contain a truss line, so like the blue line within its boundaries. This defines how thin an arc can be, at least conceptually. The image that you see here captures the limit. A thinner arc would fail instantly. Sorry, jumped to. But thinner arc would also use less material. Hence, finding a good shape was always important. This was also known to the master builders of the past, and it is often said that Gothic construction was especially daring. It means that those arches were very slender. I was interested how close the builders got to the theoretical optimum. I studied the pointed arc and determined its optimal shape, which is the shape that results the thinnest possible arc for a given load case, in this case, self-weight. And I proved that the form exists in an analytical way, which supported previous numerical studies. Then I turned to a kind of data-driven approach because I was interested that it's nice that we know what the optimal shape is, but how common that was in the past. So what I did is, first I looked in the literature, what are the typical shapes of Gothic arches? And there are some construction methods. They always define an arc based on their eccentricity. The eccentricity is basically, you see on the left, black dots. So the eccentricity is basically the distance of these black dots from the center of symmetry of the arc. The biggest the eccentricity, the pointier is the arc. So I collected data of various arches from English and French Gothic cathedrals and measured their eccentricity and put them in graph, as you can see. I also included the ideal shape of an arc, that's the black dashed line in terms of eccentricity. And I also included the so-called typical ways of constructing Gothic arches, the 5-point arc, the 4-point arc, or the 3-point arc. These are marked in dashed orange in the image. As you can see, there are two things we learned from this and haven't seen before. One is that, yes, the Gothic masters were very daring because there are some designs that got very close to this black line, but they were also they are also not too close, which means that safety was considered, and that's reasonable because there are more than one load case in real life situations. The second, and I think in a way it's more important, is that there are quite a few dots that do not match either line, meaning they do not match the orange lines either. That means that we have an assumed knowledge of how these arches were constructed, what was the geometric method, but in reality, the arches that are built do not really match these data, so further research is probably required to know how they were actually constructed. Okay, interestingly, not only the global geometry, but also the shape of the voussoirs, essentially the shape, the bricks or the stones that make an arc, affects how thin this arc can be. Moreover, these two features, global shape and voussoir shape, is interrelated. There have been studies on how different voussoir shapes affect the thickness of an arc, but no one looked specifically for the shape of voussoirs that would result the thinnest possible arc. For the sake of the research, we were only considering circular arches. I developed an optimization methodology to find these voussoir shapes, and you can see the result on the right. What you can see from this result is that those voussoirs are very strangely shaped. The important thing is that some of them are very steep, and that means that they might slide in actual situation, given that they are built from realistic materials. So we also conducted some large-scale experiments to see how they work. And as expected, some of those experiments turned out to be rather thought experiments because those arches do not stand. This highlights the importance of friction, which is usually not considered in truss line analysis. But I found a way to incorporate friction in a geometrical way into the same framework that I developed to find the optimal shape of voussoirs. And again, those investigations have some interesting conclusions. One of them is that it explicitly tells us why a typical voussoir shape, which would be radial, as you can see on the top left yellow image, works almost for any arc. The reason is that for reasonable material qualities that masonry has, this shape is always above the limit of friction. But there is another thing which is interesting. From this investigation, it turned out that for flat arches, these do not hold. It means that for flat arches, we would need to specifically design the shape of the voussoirs to avoid sliding. And there is another thing which is not directly related to friction, but you can see from the image on the right, these curves, the red, the black, and the blue, are limiting curves of the thickness of an arc subject to their global shape. So from the left, we go from a pointier one to a flatter one on the right. And observe that the highest values of these curves, meaning the biggest thickness, is almost at the same place where there is the semicircular arc. It is very interesting because it means that the semicircular arc is in a way the worst possible shape we can choose for an arc, and yet we build so many of that. So that's the background with which I arrived to the form finding lab, where the challenge is to find ways we can reduce or even eliminate the need for formwork and scaffolding. This is relevant because there are many studies in complex wall shapes, free form walls, and they usually require quite a lot of formwork. So we studied various vernacular and historical methods. You can see a few listed on this image, from corbelling to Catalan vaulting, Nubian vaulting, cable staying, rib networks, and plate band, from which I'm focusing on the pitched brick technology. This is a technique that originates likely from Egypt or the Middle East, and the previous image tells why it works without formwork. Essentially, it needs heavy back support. Usually, it's a wall, and all the layers are laid a bit inclined, so they are always supported by the previous layer, which eventually lays on the wall. Despite how ancient this technology is, we still know relatively little about how it works, especially how the forces are distributed during construction, which would be interesting if, for example, we would like to remove the wall from the end, or if we would like to find the ideal shape in terms of angle of inclination, global arc shape, etc. So this is the kind of research we are pursuing now. Okay, and now let's start to talk about shells. And from all the shells, I will first tell you about the history of the Zeiss-Dywidag system. This was a very successful innovation in the pioneering period of reinforced concrete shells. And it had a long-lasting effect on both the technological and the theoretical aspect of shell buildings. The Zeiss-Dywidag domes were built all over Europe and even overseas before the Second World War, partly because this technology was sold along Zeiss's newly introduced projecting planetarium. The name Zeiss-Dywidag comes from the name of two companies. Zeiss is a company that specializes in optical devices, and Dywidag is a construction company that specializes in reinforced concrete construction. The story started here in the middle with the red dot with the red circle around it, which is Jena, and it is in Germany, and it started in 1923. RC shells, reinforced concrete shells, are made of concrete plus reinforcement. Most commonly nowadays, formwork is laid, then reinforcement, and then concrete is pulled over it. This was not obvious in the early days of shell history. In a way, the history of reinforced concrete shells, at least in the Zeiss-Dywidag system, started out as grid shells, meaning that first, without any formwork, the self-bearing grid was constructed. This is essentially the reinforcement of a reinforced concrete shell. And then, when the grid was already made, then they laid light formwork, and on that light formwork, they sprayed the concrete. This was true for the first two stages of development of the Zeiss-Dywidag system, and then they changed the whole way of construction and started to build shells as we do reinforced concrete construction today. So making a formwork first, then laying the reinforcement, and then pouring concrete over. It was rather easy to explain this last step. I mean, why this last step was taken. There are two main reasons. One, the second method, the non-bearing grid, requires less precision. And the concrete layering can be a bit thinner, which, if we think about it with what we know about concrete construction today, is a bit absurd, because the thickness they were thinking about is really 3 centimeters versus 4 centimeters, which is extremely low for concrete construction. But back in the early days of shell construction, it was not unusual. So I will focus on the first two phases, which is building the reinforcement, so the self-bearing grid first. And there were 2 steps. The first one was a geodesic pattern. There was only one dome that was constructed like that. That was the first planetarium of Jena. And it was followed by a Lamella type of topology, one similar that is captured on the image on the right, all the later planetariums were constructed according to this logic. Geodesic patterns are highly regular, and they also appear in nature, for example, in radial areas, in viruses. There are many types of them, and the differences of the pattern does matter. Related problems occur in geometry, biology, geography, and there are more. In architecture, their pattern influences how uniform we perceive them and how many different edges are used for their construction. I will first tell you about the intricate pattern of the world's first ever built geodesic dome, which is also called the Miracle of Vienna, and its designer, who was Walter Bauersfeld. Walter Bauersfeld was a chief engineer at the firm Zeiss. He was a mechanical engineer by training, and his main field was optical devices. So this was a really new field for him, but he really made important contributions to this field. If you know the term geodesic dome, most likely you associate it with Buckminster Fuller, who was a very famous innovator at the mid-century United States. And he was the one who coined this term, actually, but he coined this term in 1948, which is more than 25 years later than the dome, where the first dome was actually constructed. We do not have any information that he had any previous knowledge of this dome, so likely these two things happened completely independently from each other. The interesting thing about the first geodesic dome is that, I mean, the challenging thing was that there was not much info on this early example. It was rediscovered in the 1980s. And then there were various assumptions made retrospectively how it was constructed. A very popular belief was that the pattern of this dome was the same as the pattern of Fuller's alternate subdivision, which seems logical, as that is a very easy to construct pattern. But there were other researchers who know the work of Bauersfeld as an optical engineer. And as an optical engineer, he was very keen on optimization. And the idea was that someone who went so far in optimization in optical devices would probably not settle to something that is easy to construct, but in a geometrical sense, as I will show you, performs rather poorly. And this idea that the design must have been different than Fuller's comes from Professor Tibor Tarnai. A brief outlook what Bauersfeld did as an optical engineer. He was the inventor of the planetarium device, this thing that you can see on the right. And actually he turned to build the dome because he needed a surface that was flat and uniform enough to try his projecting device. The projecting device also relies on a geodesic concept. It's the projectors are inserted on the surface of a truncated icosahedron, and he made sure that each surface would fit the same inscribed circle, because that would mean that he could get the uniform projection that he was going for. So now we know why he designed the dome. We have also saw a couple of geodesic domes or geodesic patterns, but there are some characteristics that are important, and I will use these terms a lot in the upcoming slides, so let's clarify them. So first, a geodesic dome is usually created by having a regular polyhedron, typically an icosahedron, not necessarily, but typically an icosahedron inscribed in a sphere and then projected onto the sphere. Whether the subdivision of its faces then follows on the sphere, or it is done on the plane and then the subdivided pattern is projected onto the surface. I will show examples for both methods. It's again not something that is set in stone, but typically each curve on a geodesic dome lies on a great circle. A great circle in a sphere is a circle that has the same radius as the sphere. In contrast, there are small circles. These are like the latitudes on Earth. So they have a smaller radius than the sphere itself. There is also the term frequency in geodesic domes. Frequency essentially means how many smaller triangles lie on one edge of one face of the icosahedron, which is the starting polyhedron of the pattern. And there is also classification of these patterns. This is that you see on the image is a class 1 type subdivision. I will shortly show you what are the other classes, because if there is class 1, there must be other classes. But based on this terminology that I have already introduced, we can see from the very few images that survived of the first geodesic dome that it was also based on an icosahedron. You can tell that from the image. It is a 16 frequency subdivision, and it is a class 1 type. What are the other classes? There is class 2 and class 3. The classification tells us if the pattern of the small triangles is rotated compared to the orientation of the original triangle, which is the face of the icosahedron. In class 1 type, it is not rotated, it has the same orientation. Okay, so that's the way to construct a geodesic dome. But what defines a good geodesic dome? There is an aesthetic aspect. It needs to be smooth, and it can be achieved with almost equilateral triangles. There is also construction and assembly aspects, which would need as few edges as possible for easier production. Why is it so hard? Usually these two aspects are conflicting, meaning that you can go for a very smooth pattern, but then you will have a greater variation of edge lengths, or you can have very few edges, but then the pattern will not be so smooth. It might be insightful to see that there are only 5 platonic solids, and these are the solids. These are the solids that have congruent faces, and all faces are regular. And even from the 5, there are only 2 that have triangular faces. The second and the third in the column. The third one is the icosahedron that we will focus on. There are, of course, not only regular solids like the platonic solids, but so-called semi-regular solids that have some properties of the regular solids, but they are a bit more varied. One of them is the Archimedean solids. Here, the number of the edges is 1, but as you can see, there are multiple types of faces, always more than 1. The dual of these solids, and there are only 13 of them, the dual of these solids is the so-called Catalan solids, which have congruent faces, so only 1 type of face, but then the edges are, the edge lengths, if you wish, are varying. So I think this is kind of insightful why this is such a hard challenge to find a pattern on a geodesic, find a geodesic pattern that simultaneously fulfills both aspects of an ideal geodesic dome. Let's see how Bauersfeld attempted to do this. First, he introduced the benchmarking parameter for smoothness. He called it edge length ratio. This is the ratio of the longest versus the shortest edge. He also aimed to have the bracedome structural behavior approximated by a membrane shell, a continuous model for calculation purposes. And for that, he wanted to have as regular triangles as possible. And what these two added up in his mind was an equal area tessellation. In his manuscript, which is the main resource for this research, there are 3 main benchmarking parameters that he continuously used. One is the already mentioned edge length ratio, so the longest and the shortest, the ratio of the longest and the shortest edge. And the number of different edges, this controls how many different edges are in the tessellation, and the so-called edge density, which is the perimeter of the triangle over, or half perimeter of the triangle over the area. While the first 2 benchmarking parameters are global parameters, so there is one number for the whole tessellation, edge density is actually local. I will talk about edge density only towards the end of this part of the talk, but it will be interesting to see how he used it. One of the most exciting outcomes of this research was that we could prove that Bauersfeld was very much into optimization. As I mentioned, there were very few resources on his work. The reason for this was that there were a couple of images that survived from this first geodesic dome. It was meant to be a temporary structure, and as such, it was destroyed 3 years later as it was constructed. It was thought that the blueprints of the design were lost, and it took considerable time for the interested scientists to learn that Bauersfeld actually had a lot of notebooks, and those notebooks are actually kept in the Zeiss archive. So all the results that you can see here are based on his notebooks, because he published very little about what he did, and even the publications are very contain very little information on the process or on design parameters. During the optimization process, he developed various patterns, and some of them are super interesting because geodesic tessellations have a very rich literature because they are so relevant for many disciplines, not only architecture. But these studies were done from the I would say, late 50s to the 1970s, actually. While those things that I'm showing you are actually created in 1920, so almost 50 years before. And again, these things happen kind of independently. So it was also kind of a surprise for the researchers of geodesic patterns that these solutions already appeared in Bauersfeld manuscript. This is an interesting pattern that he developed. It is interesting because it was independently from him, developed also in the 1970s by 2 scientists, Pavlov and Tarnay. This is a pattern that has a good trade-off between the edge length ratio and the number of different edges. It also reveals the depths of Bauersfeld approach, the theoretical depths of his approach to optimization. Why? What you can see on the image is a 1/3 of the face of the icosahedron down here. And this pattern is constructed as follows. This is the original edge of the icosahedron. It is divided in this case to 8 equal parts. So it will be an 8 frequency subdivision. And from the middle of the second part, the height of the triangle that will be constructed here is measured up, and on this and where it crosses this symmetry axis, that marks the point of the vertex of this isosceles triangle. So the concept is to make as many isosceles triangle in this system as possible. The logic continues as it starts here. And when the tessellation is done, then it could be analytically proven that there are 2 edge lengths that has to be considered if we want to get the ratio of the maximum and the minimum edges. And independently of the frequency, these are always the same. There is one F-type, which is the kind of horizontal one, and the H-type, which is the inclined one. the ratio will come from the maximum of this H and the minimum of this F. The ratio depends on the frequency. The greater the frequency, the greater the ratio. But there is a limit. It is not necessary for every tessellation to have a limit, but this tessellation has a limit. And this limit was determined by Pavlov and Tarnay in the 1970s as 1.284. And I was shocked to find it in the manuscript with the exact same value. The only difference between Bauersfeld approach and Pavlov-Tarnay's approach is that Bauersfeld seems to find these two, the location of these two edges, the H-type and the F-type, empirically. So he found out that the location of those were kind of fixed, independent of the frequency. And that's how he developed the limit, while the two scientists later also proved that these were actually the location of the maximum and the minimum edge lengths. Another approach that Bauersfeld take, and then also a lot of others, is called side bisection. In this case, the original face of the icosahedron is first projected onto the sphere, and then the midpoints of the edges, marked here black, are connected with great circles. And when we have these new edges, again, the midpoints are connected with new edges, with great circles on the sphere, and so on and so on. This is also a pattern which has nice geometric parameters. Bauersfeld actually attempted to reach an equal area tessellation with this method, which was not, he was not happy with the result, although it's not very far from an equal area tessellation. It also has relatively few edges. It's debatable, but not that many at least. And it has a very good edge length ratio. But neither was the one that he was actually settling on. I've considered myself super lucky when going through this manuscript, an insert kind of fall out. And in that insert, I find a very detailed calculation of a pattern that at first I had no idea what it was, but it seemed very promising. It also contained a lot of calculations. And while I already told you that Bauersfeld's aim was to find an equal area tessellation, this was not obvious at first. No one told me that it was so. So when I saw the calculations, I had no idea what I'm seeing. But after a while, it became obvious by re-engineering the calculations that he was actually developing an algorithm that would lead to an equal area tessellation of the geodesic surface. It is not, again, a perfect match, so it will not result equal area triangles 100%, but it is a very good algorithm to almost get there. The algorithm works as follows. Again, what you see on the image is not the 1/3, but the 1/6 of the face of the icosahedron. Remember that the face of the icosahedron is a regular triangle. So 1/6 of it actually represents the whole triangle because of its symmetries. First, he divides this triangle in the area ratio 1:3, and then with every subsequent step, he halves the area. These steps are marked in blue here. This was a very interesting result. It could be understood, as I said, by the calculation. He used the so-called Lie formula to calculate the area of a spherical triangle, which is calculated as the spherical excess. It means that the internal angles of a spherical triangle do not add up to 180 degrees. They are always more. And how much more actually means the area of these triangles. Okay. Yes, I just checked the chat and I see that you're encouraged to ask questions, and I also encourage you to do so. I only ask you that please just let me know, so don't put it in the chat because I'm not checking that regularly. just tell me if you have any questions during the talk, and I will stop and explain, or try to explain. Okay. I said that this was not leading to an equal area tessellation, and I'm trying to explain here very briefly why. The steps with the blue arrows from the previous figure, they properly have the areas. They are always resulting equal areas. That's fine. But when you are done with those steps, then you are still having kind of big triangles that you likely want to subdivide more. And then there is a problem, because if you want to subdivide, for example, this triangle into 4 equal area triangle, you will find that it's not possible. The reason for that is that you can constrain, for example, these 3 external triangles close to the original vertices to have the same area, but you cannot constrain them to, but you cannot constrain that area must be 1/4 of the big triangle's area. There is no solution if you pose that problem like that. And it turned out that Gaspar was fully aware of this. Actually, all triangles that have a slightly different area than would be ideal, or that would come from the equal area concept, are marked in this tessellation, and the difference is calculated. So at first, with this method, he reached, as you can see on the left here, an 8 frequency tessellation. And in the final step, it's not clear why, he decided to subdivide it further and eventually landed at the 16 frequency subdivision that I have shown at the beginning. Strangely, this last step was different from the ones before. It was based on the side-by-section method. I will show you what it meant in terms of geometrical properties very soon. But first, I said that it was not 100% equal area, so let's see how it performed. You can see a color-coded map of the areas of the resulting tessellation and how they result to the ideal. The scale is on the right. The scale is in percentage. So it means that the higher deviation from the ideal unit area is 12%, but that happens very rarely, basically only here around the edge of symmetry. And typically the deviation is under 1%, which is a very, very good result. If we would do that, for example, if we would use a computational approach, and if we could get the triangles to be close to the equal area within 1%, that is already considered a very good result. Okay, so let's compare and contrast. The Bauer-Feld type subdivision is the equal area subdivision, as I have shown you, with the last step having side-by-section and not the method that he originally started, or not the algorithm that he originally started to use. We also calculated the geometrical data for an unmodified logic. So if he were to continue with the same algorithm, as a comparison, we included the side-by-section and Fuller's icosahedral subdivision because that was originally assumed for this subdivision. As you can see, E marks the number of different edges, T the number of triangles in subdivision, and nu marks the edge length ratio. So the Bauer-Feld type has relatively few edges with the last step having the side-by-section. It is only superseded by the side-by-section, which has even fewer edges. But in terms of edge length ratio, the Bauer-Feld type, so the equal area subdivision, is by far the best. We have calculated these values for the 16 frequency dome, which is the same as it was built, but we also calculated them for the 8 frequency dome, which was one step before. There are differences in the values, but their relative positions do not change. There is only one thing I wanted to highlight. I spent quite a lot of time to explain this Bauer-Feld Pavlov-Tarnay type, which was the first I have shown you before side-by-section. And I said that they have relatively few edges. And look here, this value is very, very low. It is only 8. While for the same frequency, an equilayer restoration would require 20 different edges, and a side bisection would require 15. The only problem was that it was a fantastic result. I was super excited, but there was no indication on the documents that this was actually the one that was built. So we did virtual reconstruction of various patterns and then compared it to the existing photographs to kind of have another proof of concept and try to support whether it could have been built like that or not. So let's see how various subdivisions perform. This is Fuller's alternate, so the one that was thought it was. As you can see, it is not a particularly good match. Side bisection is already more promising, so the red overlay is almost matching the one underneath. And this is Bauersfeld's, the one that I call Bauersfeld type subdivision, and I think with some reason, because this by far matches the historical images the best. Okay, so I spent the previous part of the presentation to convince you that this geodesic pattern is awesome, and it really is. In geometrical terms, it performs very well. So it was super interesting to see that after this, only this first dome was constructed, the method was left, and for the tessellation, another kind of pattern was chosen, and that's so-called Lamella type dome. The difference between the two is that the geodesic is based on a regular polyhedron, which is projected onto the surface, whereas a Lamella type dome is essentially uses small circles as latitudes on Earth, and then isosceles triangles are constructed within these small triangles when the pattern is finalized. What could have been the reasons for this change? One reason was that the later domes were significantly larger than the original dome, which was only built for demonstrative purposes. The original dome was 16 meters in span. The second dome that they built was actually 40 meters in span. So that's one reason, because a bigger dome requires a different construction technology. The original dome was constructed from top to bottom with the help of a crane. The later domes were not surprisingly constructed from bottom to top without the use of crane because of their size. So that could be one reason, but there is one that is more important, I think. If you look at these images, what they try to show you is the patterning as you would lay them if you were on the work site. Check that for a geodesic dome, you will have to vary at least 1, 2, 3 or more types of edges in one row. Whereas for a Lamella type, you would use the exact same type of element in one row, and you don't have to think which one comes next. That's one thing. Then there are other properties. Of course, there is the edge length ratio, but from constructional purposes, it is really irrelevant. But the different number of different edges, which is marked with E, is important. For a Lamella type of dome, for the size of the later domes, so approximately 40 meters, there are 88 different edges. In a geodesic pattern of the same size, there would be 800, so a lot more different edges, which from a constructional point is not good. However, the geometry of the geodesic pattern is really nice. The question if the Lamella type could match it. First, we learned that the Lamella type was also based on the idea of trying to create equal areas. So we checked how far Bauersfeld got with that. He wanted to have relatively regular triangles because he wanted to calculate the behavior of the shell based on a continuum model. And for that, he would need regular triangles. To have a good match between the two models, discrete and continuous. And again, he used some benchmarking parameters. In this case, he used, to some extent, edge-length ratio, not so much. Rather, he resorted to the number of different edges and the edge density. Again, that's a local parameter and is the ratio of the half perimeter over the area. I told you that I wanted to calculate the behavior of the shell using a continuum method, and it has a name. It's called the equivalent shell theory. The concept is, as Bauersfeld used it, that what would be the equivalent continuum of a regular grid of bars that is a triangulated grid made of regular triangles. So what would be the equivalent continuum that would have the same deformations? His model was a planar one, so he imagined two planes loaded in their own plane. And what would be the properties of these two that would result similar behavior? Why was it used? The calculation of bar forces is actually possible in a triangulated grid using the equivalent continuum as a base, based on statics essentially. So for that, you would not need to worry about the deformations because the problem is statically determinate. But the deformations are relevant if you want to use it for buckling analysis. And actually, this is what Bauersfeld intended to use. He wanted to use the continuum method for to check if the shell were prone to buckling. The grid shell was prone to buckling. And for that, he needed the assumption of equal deformations. Not only the assumption, he needed to make sure that the deformations were actually equal. The equivalent shell method or model has a rich literature. It started in the 19th century with a very basic model. I will shortly talk about it. But there was an inverse problem that was investigated around the time of Bauersfeld. That's called the truss framework method. This was an approach to calculate stresses and strains in a continuum based on the discretization of this problem. This was essentially an early numerical approach. This table is here to provide you an overview of what happened in the time of Bauersfeld and before him and after him. So you can kind of contextualize his contribution to the equivalent shell theory. His work was done in the 1920s, around 1923. The equivalent shell as a concept already appeared in Schwedler's and Föppel's studies. They were also working with grid shells, but in the original form, they only used it to calculate bar forces. So deformations were never considered. From the same time period, other studies that considered an equivalence were always focusing on the inverse problem, so on the truss framework model. The equivalent shell theory, as Bauersfeld used it, so using a continuum to calculate calculate buckling or bar forces in a grid shell, was actually became heavily researched in the 1950s. And there is a seminal paper from Wright, but that was in 1965, that in terms of content is comparable to what Bauersfeld has discovered in 1923. So again, he was a mechanical engineer in an optical form. This was a side project for him, but his contribution was only matched like 40 years later, which is, I think, kind of exciting. The first dome that he designed with this Lamella pattern is the so-called shot dome. It is also in Jena, where the first dome was built. This is not a coincidence. The headquarters of the Zeiss company is in Jena, and Schott is the neighboring company, and the two companies collaborated a lot. So for this company, he designed a large dome with 40 meters span, and he designed a lamella type of tessellation. The lamella type of tessellation has a unique challenge that normally, as you would approach from the border to the middle, the triangles would become more and more distorted because there are less and less space, if you wish. What Bauersfeld did is he developed a scheme to reduce the number of triangles subsequently from the edge of the sphere to the middle of it. This was again re-engineered from his original drawings that you could see on the last image. From the calculations, we could determine what kind of constraints he used in terms of the shape of the triangles. So what were kind of the limits that he allowed in terms of distortion within the same range. The range is in light black here, and in bold black, there are the so-called jumping rows. A jumping row means that there is a reduction of the number of triangles. There are irregular vertices there. And from then on, again, a different range is defined. Within a range, the number of triangles in each row is always the same. It is also interesting how he determined these ranges globally. He wanted to have equal area triangles. And he said that, okay, in order to have equal area triangles, I will do the following. I will determine the height of the rows, the vertical height of these rows as being equal within one range. And the ranges will have heights, vertical heights, that are reflecting how many triangles they are containing. Why did he do that? Because when you calculate the surface of the sphere, of a strip on a sphere, sorry, you calculate it using the radius of the sphere and the height of that strip. So this was a way for Bauersfeld to make sure that the triangles will become sort of equal area. Again, his method did not result in equal areas, but it got pretty close. But how close? First, we will focus on the global parameters. So kind of what were the ratios of the largest and the smallest area, edge length ratios, number of triangles, and so on. And then I will talk a little bit about local parameters. What are the subdivisions, that tessellation types that are compared here? There are geodesic patterns and lamella type patterns. The geodesic patterns here are made up. He has never made a design for a geodesic pattern for this size, but we try to fit one as close as possible. And the logic of the fitting was to have the same amount of triangles around the edge of the sphere. The lamella type, there are two. One is based on this equal height concept that I briefly introduced before. And the second one is the equal internal angle. And this is something that you would do, I think, if you were tasked to design a dome. This is something that seems logical, to have each row have the same internal angle. Let's see first how the ratio of the largest and smallest area works in different patterns. As you can see, for his design for the lamella dome, the ratio is 1.6. For geodesic patterns that we tried two, one based on the full area design and one based on the side bisection design. One performs significantly better, so side bisection results much more even distribution of triangle areas, but the full area design is way worse. Interestingly, the one that is simpler to construct and it's also a lamella type of design, the one with equal internal angles has actually a pretty similar ratio in terms of maximum and minimal areas. When we look at the edge length ratio, so which kind of measures the smoothness of our tessellation, what we will see is that no matter what we do, the geodesic patterns are always smoother than the lamella type pattern. Is marked with E. You can see that for a lamella type of design, for the whole dome, there are only 88 types, while for a geodesic pattern, there the number is in the range of I promised that I will talk about his another benchmarking parameter, which is marked D, and it is the edge length ratio. He tried to derive global parameters because edge length ratio goes for each and every triangle in the subdivision, and there are different. And the global parameters are sort of a similar logic that what he did, for example, with the edge length ratio. He chose the largest value and the smallest value and checked the ratio. You can see here that in this sense, the result what you get is pretty similar what you get from the edge length ratio, which means that the globalized D values work pretty much as a measurement of smoothness. But what they can do as global parameters. As local parameters. There is one D value, so there is one value of perimeter over area for each triangle in the tessellation. This is shown in the map. Ideally, if the areas were the same, it's easy to see that the larger this value is, the more distorted the triangle is. The slight problem is that here not all areas are the same, but they are sufficiently close to derive some conclusions based on this drawing. What you can see here is that there are major areas with very purple colors. The purple colors mean very high values of the D number. Here, and up there. As a comparison on the right, you can see the bar forces, the differences of the bar forces derived from the continuum model and from the discrete model. And where there are red dots, it means that there are a big difference between the values derived from one model and another. Check that the location of these red dots is pretty much the same as the location of the distorted triangles as indicated on the D maps. This is sort of expected because, as I said, the basic concept of equivalence between continuum and discrete model was that it assumed that the triangulation was regular. So where we have distorted triangles, the two models should not fit so well, and they really don't. So in this sense, this benchmarking parameter that Bauersfeld used on a local level is very much useful to indicate where we can expect a deviation between the behavior, where we can expect deviation of behavior of the continuous shell and the discrete grid shell model. This is the lamella type of tessellation, and you can also see here the geodesic one. The geodesic one has a very different distribution of areas, hence the very different coloring. What is still informative is that there is a very high contrast between purple and blue down here. And if you check again the differences of bar forces from the two models, red indicates that there are big differences. These big differences are pretty much in the same area where the contrast is very huge between the two colors, so purple and blue. Okay, and on that note, we sort of arrived at the end of the story of the Zeiss-Dywidag shells. And I would like to continue with the Hungarian shells, but I do think that here we would all need a short break. Do you agree, Philip?
Yes, thank you.
All right.
Yeah, I think maybe a short break is better for all the students.
Okay.
I think it's really interesting about your lecture on the talking about the dome, including Lamella and the Geodesic. I think the difference between them and the optimal solution, which is super interesting. I think if students have any question, maybe we can put forward at the end of your lecture. So the short, maybe 5 to 10 minutes. Okay. Okay. Coming back very soon. Hi, Orsolya, shall we start?
Yes, we can.
Great. Okay.
All right. So, okay. So in the second half of the lecture, I will talk about Hungarian shell architecture. And luckily for us, it has many links to the Zeiss-Dywidag system. So the first half was not useless. But on this starting slide, the person you can see is Piero Gennari. He was a very famous structural engineer of the 20th century. He significantly contributed to shells, but also to prefabrication, or specifically to prefabrication of shells, on-site prefabrication. And that part is also very relevant to Hungarian shells. That is why he is included here as a, I would say, a rather important influence and reference point in this regard. All right. So first, I will tell you a little bit about Hungarian shell architecture in general. Hungary is a small country. The shell architecture in terms of the global developments is a small story. The reason why I still think it might be interesting, because it is a story of how periphery relates to the center in a way, and also, as said in the introduction, it is very much a story of how to respond to shortage. These qualities, I think, makes this otherwise local story maybe also globally interesting. In order to be on the same page, there will be a very, very short introduction to the theory of shells, nothing very complex, just to make sure that the basic concepts are introduced. Then I will discuss essentially case studies based on typologies. These are rather freely chosen. One is series of shells. So when the roofing consists of shells that have the same shape and they are laid out in a series. That will have a specific focus on praxis and how full-scale models were used. Then I will talk about hypers with a focus on technology, on-site precasting. And finally, I will talk about central spaces, covering of central spaces with shells. And the focus will be on theory and specifically on the theory of form finding. And I will introduce you to the so-called pelican membranes, which is a special kind of shell. Before all of that, I will give you a short glimpse into the background of this research. So you can see the map of Europe here, and Hungary is the tiny country neighboring the green country, which is former Yugoslavia here, and the gray country, which is Austria, all laying on the edge of this very dark black line. This is the former Iron Curtain, and as you can see, in the era that we are discussing in the 20th century, Hungary was belonging to the Soviet sphere of the interest. So the developments of Hungarian shell architecture are interesting from the point of view of knowledge transfer, because despite of the name of the Iron Curtain, knowledge transfer was possible, and it was also practiced through the curtain as well, in both directions. Of course, not with the same intensity, but it still did happen. When we started this research, this was the aim was to document Hungarian shells, because they are a huge part of our heritage of industrial construction, but they are also a huge amount of concrete. And that's important because if these structures, which are reaching the end of their life cycle, are being demolished, they will create a large amount of rubble. And they are very likely to be demolished unless public awareness of their value becomes like the norm. And these structures are really not known, not even within the profession, let alone the public. So it was kind of an important mission to make them known, tell their stories, and hopefully help to conserve them instead of destroying them. While we collected data on these shells, we started to recognize patterns. We started to recognize similarities within the borders of Hungary, but also with some international examples. And that was very interesting. And we started to focus on if we can prove that that certain influences existed. How can we show that certain connections and certain ways of knowledge transfer were possible? The direct outcome of our documentation efforts was an interactive map where we located the shells in Hungary, included some basic informations, images, and recorded the current state of these shells. We also organized an exhibition, as it was already mentioned in the introduction. The exhibition was titled Frozen Modernity, and the reason why this exhibition was created at the time of 2016 was that there was a traveling exhibition on the work of Nervi that was coming to Budapest. And that was a great opportunity because Nervi is someone that is very well known. So using his work as a kind of context to which Hungarian shell architecture could be exhibited, a context within which the Hungarian shell architecture could have been exhibited was a good opportunity for this exhibition. Okay, so what makes a shell Hungarian? David Billington, in his book Tower and the Bridge, introduced the concept of national schools of shell design. The national schools he identified was the German, the Spanish, and the Italian. These are basically roughly the three columns you can see here. German being on the left, Italian in the middle, and Spanish on the right. He argued that the German school was a very analytical, was very strongly based on analytical methods. They used mathematical models, usually closed form solutions, to define the shape of the shells. Hungarian designers did basically the same. That's partly because of their education. German traditions had a very strong influence on Hungarian education, so they are very much related to this school. On the other hand, we have the Italian and the Spanish national schools, which are more building upon intuition. Some of the shapes were determined by model building, and form finding methods were not analytical, but either physical or maybe graphical form finding methods were much more widely used, and are still more widely used today. This is a kind of a formal conceptual background, but there is also a temporal difference between how shells were built in Hungary and other parts of the world. This is 1957. It's an important date, at least within this topic. This was the date when the first shell in Hungary was built after World War II. And the funny thing is that by the time it was built, the history of shells was almost over everywhere else in the world, in the sense that engineers already realized that while shells are super efficient structures, in industrial applications, they are still not always economic because they have very high cost of construction. And that's why Ove Arup, a very famous British structural engineer, declared in 1957 that the so-called honeymoon period of shells is over. At the same time, it was told about Hungarian shell architecture that shells are not characteristic in Hungary. The large span industrial buildings are usually solved with prefabricated concrete frames or Firendel trusses. So there was a kind of lateness in how shells were built in Hungary compared to other parts of the world. And this is also captured in this timeline. The contribution of Hungarian engineers is on the right. And some famous examples are on the other columns. What I would like to highlight, though, is that there were significant building activity before 1950 in Hungary, before World War II in Hungary, and that is quite interesting because that is very much in the pioneering period of shell building, some of them overlapping with the first trials of the Zeiss-Dywidag system. To put this timeline in a more in a different visual interpretation, these are international examples of shells. Some of them probably you also know. For example, the one on the second row, the third from the left, is the Olympic Stadium in Rome, which became an icon, not the least because it was the very first Olympic that was aired real time. And this is a structure that was actually built by Norway. The buildings are put here based on when they were constructed. And if we now look at the timeline filled with Hungarian examples, you can see a very big empty space here. This is the period after World War II when shells were not built in Hungary. And that was the direct result of timber not being available. And the formwork of shells would have needed timber. To put it more dramatically, look at the image on the top right. That's a church. That would have been like the crown jewel of pre-World War Hungarian shell architecture, but it was never completed. The scaffolding was already there, the formwork was already done, but then the war came, and actually the scaffolding and the formwork all was used for other construction purposes and also to some extent for heating during the war. And it is still in this state today. So it was kind of never finished. In a way, it kind of reflects the story of Hungarian shell architecture in one particular example. Okay, with the red, I highlighted some structures that were designed by the same person. This is István Menyhard. The name is not very important, but it is important that also in Hungary, there was one figure who was very influential and who had a long-lasting effect on shell design. This was very typical in the pioneering period of shells, not only in Hungary, but also other parts of the world. I promised a short intro to shells. I just want to classify structural models and geometry very briefly. For structural models, when we talk about shells, and these are continuous shells, we usually differentiate between three different types, from the very specific to the more general. We have shear-free membrane on the top. As you can see from the arrows, shear-free membrane is a membrane that has that only has normal forces in it or normal stresses in it, so no in-plane shear either. This is a very unique state. It's not very typical. Where you can kind of experience it in real life is more tensile structures. They are typically modeled as shear-free membranes. But it can also be applied to reinforced concrete shells if the form is defined accordingly. Then there are membrane shells, which means we have normal forces and also in-plane shear forces. And the most general case is shells in bending, when we have normal stresses, shear stresses, and also bending moments. The majority of structures I will show you is was based on the design, was based on the theory of membrane shells. So usually they assume that there are only normal stresses and shear stresses, and they wanted to create forms that would work like that. In terms of geometry, there are shells which have an elliptical shape, like on the top, a parabolic shape in the middle, or a hyper shape, which is at the bottom. The shapes are classified based on their Gaussian curvature. Because in Hungary, there are not many complex shapes, they are usually closed form shapes. The Gaussian curvature is the same at every point typically, and that's why they can be classified globally as elliptical, parabolic, or hyperbolic. Okay, so now we will see some examples. First, some examples when there was a big roof structure and it has a series of shell, and a series of shells makes it up. The first example is from the pre-war era, from the designer I mentioned, so István Menyhard. This is the bus garage. It's a typical application of shells. It's an infrastructure, a building for an infrastructure, which requires much bigger spans than was used before. This structure is exciting because it has a 90-meter span in the lateral direction. It had the shells are elliptic. I mean, each slice is elliptic. This 90-meter span was quite large. It was spanned with a 6-centimeter thick shell, which is extremely light. And this was the biggest span that was built at that time all over the world with this kind of structure. It was only paralleled in 1952 by the Marnian hangars, which were designed by Nicolas Esquilin and Auguste Perret. From this image, I would like you to mark these transversal girders that are visible here. These girders are not visible on the previous images, but they are there. And the reason that they were put there is that when these shells were constructed, during the end of the construction, the contractor asked the engineers to come to site because there were some movements which he was very much not confident with. And it seemed that the shell suffered some deformations that were out of range of design. And the experts that came to the site finally decided that it must be reinforced. And as a reinforcement, they built in similar transversal girders, as you can see here. The story is interesting because this was one of the first shell structures that were built in Hungary. It was designed by someone who has never designed shells before. I really like this image because it tells us in a figurative way what it must feel like to do something that no one has ever done before. So it's kind of leaping into the unknown. And that's what was happening here. To see how it evolved, this design, you can see this design here in the middle. Before that, the designer István Menyhard used to design bridges, arc bridges, and you can actually notice the logic of bridge design here with the series of arches. You can imagine them as kind of bridges in themselves. Another important influence which we know was there was a design from the Zeiss-Dywidag company, so the same company I was telling you before. They not only did domes, they also did barrel vaults. And they did a huge project with barrel vaults also in Budapest that was known to this designer, and he kind of exploited that design as well when he did his own. Okay, Menyhard, so the designer of this structure, was actually the person who designed the very first structure after World War II. He was very much pushing the agenda of shells. He put up a great fight to prove that they were very economic, despite all that was said on the said against them. This is the structure that was built in 1957, the first ever after World War II. The construction technology is very inventive. it relies on a sliding framework, and for the framework, for sliding the framework, they use the overhang frames that were actually later used in the factory. So they kind of exploited a technology that was already there to make the formwork as efficient as possible. The shape of this roof is very interesting. It is a saddle shape. As you can see, between two girders, there are these saddles. And these saddles on the sides, on the shorter sides, they are connected to conoids because along the edges, they wanted a horizontal line to finish the design and not they did not want it to see the edge of the saddle. But this is a challenge because normally you would have to support a saddle shell with edge beams all over the perimeter. And a typical saddle would also exert normal stresses in all directions. But if you choose the dimensions of the shell right, and by right, I mean, for example, the ratio of the longer and the shorter side is 1 to 2, as was the case here, then for certain load cases, and the design load case here was a uniform vertical distributed load, and for that load case, as you can see from this image, the shell would only the shell could be supported by edge girders along the long edges, and it would only only normal stresses would exit on the short edges. So only these normal stresses would load the conoids adjoining them, and that's actually a load case that the conoid is very happy with. So this was a very creative concept on how to solve an architectural problem, but also how to make it suitable for a very specific shell geometry. This was such a success in terms of efficiency that it generated a large number of shells, all industrial application, which were sort of related to this original concept. While it was a saddle shell, which is a hyper shape, the later structures were almost all of them elliptical. The reason for this is many had thought that this would be beneficial to fight buckling. While that was right, in terms of construction, eventually they figured that they can save even more money if they would go for these elliptical shapes, and that's what they did in later designs. This is an early successor of the saddle shape. This is also a saddle. They tried to combine it with some skylights in a unique way. This is one example of the same concept, I mean, same constructional concept, but with an elliptical shell design. I said that here we will focus on Praxis. Since this was the first shell that was built after World War II, the client wanted to make sure that it is actually doable. So in addition to the calculation, he also ordered a full-scale model to be built on site. It was done, but there were multiple problems. First, the contractor was pretty inexperienced, as you could imagine, the reasons why. It was also done in the winter, so it was very cold, which is not ideal condition for concreting. The inexperience of the contractor led to two things. The material quality was not controlled well enough, so poorer material was used and was designed. The formwork was also not done according to standards, so some parts of it sunk during construction, which led to the uneven distribution of material. The original thickness was already very small, 6 centimeters, but in some places it also became less. And eventually this mock-up, so this full-scale model, so it failed. And there was a huge investigation to figure out whether it was an engineering or a constructional defect. And while it concluded that it was a constructional defect, the reasons were never truly clarified. It was an interesting project for master thesis, where the student recommended built a parametric model to investigate different load cases and check which was the most dangerous for this shell, whether the poor material quality, the uneven distribution of stresses, or the change of the original geometry was the fatal factor. The conclusion is, which was kind of surprising to us, is that the shell could take almost everything. It could take a different geometry. I mean, it could still stand with a different geometry. It could still stand if the thickness was uneven, but it could not stand if the material was worse than it was designed for. Now we move over to hypers. The move will be not very drastic because the last example we have discussed is already a hyper shape, the saddle shell. But we jump back in time to 1938. The date is interesting because the first study on hyper shells, which was a paper, was done in 1936, so 2 years before. It was done by a French engineer, Ferdinand Aimond. He was the first who clarified the behavior of hyper shells. And after 2 years, the same engineer, István Menyhard, built such shells in Hungary only based on the studies. These shells were among the first in the world to be built with this hyper shape. There were 2 others, one in Italy at the same time, Giorgio Baroni, and of course the inventor Ferdinand Aimond also built hypers in France, but these were very early examples. After World War II, there were also hyper was also a popular form not only in Hungary but everywhere else in the world. You can think of Felix Candela, for example, who was very famous for his hypers. In Hungary, many hypers were built to serve as support infrastructure. Bus stations, train stations were often covered with hyper shells. These designs were standardized, and they were a good field to test prefabrication methods, specifically on-site precasting. And you cannot talk about on-site precasting without mentioning Nervi. Nervi developed a very intricate system of on-site precasting that is named Nervi system. It builds on the following. Nervi was inspired to do this because there was a lack of steel in Italy in the 1930s when he wanted to build his first shells. So he wanted to develop a technology which requires, it still requires steel, but it doesn't require the regular steel bars. It instead requires kind of a steel mesh, which was available. For that, he developed a new kind of concrete, which is called ferrous cement. It is also concrete, but with a very fine aggregate. As a formwork, he used different things, but in these images, what you can see is the so-called rhombic tabelloni. These are small-scale prefabricated elements. The method or the whole process can be described as kind of an artisanal prefabrication, which some with some malice said it's like a fortunate coincidence of a high level of craft which was available in Italy, but with a low level of technological advancement. This is something that was very much true for Hungary as well. So it is interesting to compare how similar methods were used in Hungary. First, there is a very direct comparison between Nervi's rhombic tabellonis and the project in Budapest, which was designed in the 1960s. Nervi was also a contractor, so he was very conscious about efficiency and economy. He used prefabrication not only to save on steel, but also to save on formwork. So he developed this technology, as you can see on the red image on the top, which necessitated only a sparse formwork, which was a great way to save timber. So it is interesting to see the image on the bottom, which is in Budapest. As you can see, there is a similar system of prefabricated panels already on the location they are supposed to be, but they are supported by a full formwork. So this potential was not exploited there. To be honest, this small-scale prefabrication was not really typical in Hungary. Instead, what was done is large-scale prefabrication. Whole panels of these hyper shells were prefabricated on the ground and then lifted to the spot by cranes. And our final chapter is on the roofing of central spaces. This is the example that I have already told you about in one of the introductory slides. It was supposed to be a church. It is the unfinished church to this day. It would have had an elliptical, an ellipse-based elliptical roofing, something in the manner of this one, but this is a much smaller scale, a less illustrious space. But this was finished by an engineer who was very much familiar with the original design for another church. This shell is also designed by István Menyhard, the hero of this talk. It is completely made of aluminium, so in a way it's not fitting to our topic today. It's not made of RC, but it's still fitting because there is a very nice invention in how it was constructed. Because it is made of aluminium, it's super lightweight. That's very useful. But in order to have it stiff enough, they used the corrugated pattern, as it is obvious from the image. And while it was constructed, strips of these corrugated panels were actually pulled to their position along the edge girders that you can also notice on the image. This was a technology that was kind of celebrated internationally. The only note, the papers published on this structure added was that it is a very interesting technology. It is a very interesting structure had it been not built so late, which was already in the 1960s, which was after the heyday of shells. So form finding of shells is something that is a very hot topic today, but it has been kind of a hot topic since at least the end of the 19th century. There are many different form finding methods. These are just basic categories. There are graphical methods, physical models like hanging models. Two notable examples historically are, for example, the hanging model made by Gaudi for the Guia Chapel that's on the top image, but it was also widely used for the design of shells. A very well-known example is the hanging model on the bottom, which was a common way to generate new forms, and it is very much associated with the name of Heinz Ischler, a Swiss designer. After graphical methods and after physical models, computational methods also were employed. They started later in the 1970s with the force density method, then dynamic relaxation in the 1990s, and sort of reaching back to graphical methods with an aim now for the 3D using reciprocal figures in the works of Williams and Bloch in the 1980s and the 2000s. So within this context, it might be interesting to tell you about Pelikan membranes. It is named after the inventor József Pelikan, a Hungarian engineer. The method was first published in 1959. This is a method to generate shear-free membranes, or pseudo-shear-free membranes, I would argue. The equilibrium condition is that the horizontal projection of the forces must be equal everywhere. As you can imagine, this means that the shell actually will not have only normal forces in it, but if the shell is flat enough, this is a kind of reasonable assumption on the behavior of the shell as well, that it will be largely shell-free, shear-free, or the shear stresses will be low enough. The way shapes were found was based on a discretized bar grid model, which is kind of readable from this image. This is a model that was built by my students last year, and the unknowns it depends on the loading that you define, what kind of shape you will get. It also depends on the horizontal forces that you can prescribe on the horizontal projection of the grid. And it leads to an algorithmic iterative numerical method. There are many shapes that has been generated with this method. In theory, it is kind of similar, or has similarities with the trust network analysis, but it was used to generate reinforced concrete shells. It has a very advanced theory, but it was rarely applied to build structure. One of the few examples is the Keramion, which is in Germany. It was designed by Neufert and Polanyi in 1971. And there was also an exhibition hall from the beginning of the 1960s that we know of. The interesting thing here is that, as opposed to the grid that I showed you before, which was quadrangular, here the grid is triangular, and the method is also applicable here. The reason I wanted to include it so much in this presentation is that we know that shells based on Pelikan's methods were designed in China, but we know nothing about if they still stand or where they stand. And it would be super interesting to me if any of you might have any information on that. I don't know if that's possible, but let's see. So let's summarize. I have shown you different structures made of masonry, made of steel, and reinforced concrete. The patterns of these structures were always very closely related to how they performed in a structural sense. The patterns also on the micro scale, on the mesoscale, and also in the largest possible scale are relevant, and they are influencing the ways structures work. This kind of explains why I choose the title Structures and Patterns. And with that note, I would like to thank you for your kind attention. And I'm happy to answer any questions that you might have.
Great. Thank you. Thank you so much. We have some students here. One question is coming in the notes. Can you see it? Orsolya?
Sorry?
Yeah. Can you see the question? We have some.
Yes, I see one. Just give me 1 sec.
Can you ask a question by yourself, Carrie? Hi.
Yes, can you see my question in the chat box?
Yes, I can see your question. I'm just reading it. Okay, so I'm happy to read that you are a student of architecture. I also have architecture as my background, so that's common ground. Well, I think
which is about digital tools.
Sorry?
Yeah. The question is about, can you indicate some possible research direction for the shell structure by digital tools?
Yes.
Yeah, I think, the lecture is super good. I think very fundamental, and also including some the first part of the lecture, which is about the pre-algorithm design for the dome and shell structure, dome structure, and second part, which is about historical modern Hungarian architecture. So I think it's a pre-digital design and influence a lot to the digital. So we're looking forward, and maybe Orsolya, would you like to answer the question from your perspective? Thank you.
Yes. So the question in two parts. One is when an architect can get involved, and what are the possible research directions for shell structure generated by digital tools. So let's start with the first one. Historically, that is an interesting question, because shells, as they were first conceived, were really the field of engineers more than architects. There were, of course, there were instances when the two were kind of merged, like in the case of Neri, who was an architect and a structural engineer also. But as the history of shells evolved, what happened was that architects started to take the initiative. I think they found these new shapes exciting from an aesthetical point of view. And this kind of gave the second boost to the story of shells. Because as I explained, from a purely economical point of view, there are very few instances where shells were economic after like the 1950s, because the labor prices started to rise, and the save in materials simply did not compensate for the high prices of actually constructing the shells in many applications. But then, because of architects, shells entered the world of public buildings, and it also kind of boosted a more expressive design language of shells, which I think was a very nice change. So this is definitely something that is for the architects to have a vision of what they want. Now to the second part, so research directions for shell structures. It is very nice if an architect has a vision, but in order for a shell to be a shell and work as an engineer dreamed of it, so work super efficiently, the shape has to be right. I think everything that has been done in the developing digital tools for shell structures was done to target this challenge. So to make tools that actually enable architects to tune the shape they have in their heads to best fit a shape that would be super efficient in terms of material usage, because it works very well. Yes. Okay, so this is the main concept, but what are the research directions? Now I will talk, well, so from the large scale, I would jump to a very focused scale, because I think, for example, the message of my research on Bauersfeld is a kind of call for a revision of all the benchmarking parameters that are used, for example, in meshing. I think the studies of Bauersfeld can directly inform that, can give new ideas how to improve meshing, which is a necessary, for example, which is a necessary step to turn a model into a structure. For example, if you want to design a grid shell, you design it as a continuum, typically with today's tools, but then you will have to fit a pattern on it. And while you do that, I think, for example, and when you do that, it is very useful to have a similar logic what Bauersfeld did, which is to have geometric rules that can reflect a good structural behavior. It is useful to have those because the environment in which you are working is most likely a geometrical environment. For example, if you work in Rhino, it is essentially considering geometry. So if you can work with geometry for a very advanced, until a very advanced phase of the design, you actually also save on computational power. And that is something I think that is a potential in the future.
Mhm.
Yeah, thank you for your explanation. So I got your idea. I think the most significant part is for architects to understand the geometry and to understand the structure. Then, they can cooperate with each other and to come up with some beautiful form and beautiful architecture. Yeah.
Yes. That's
so thank you very much.
Thank you for your question.
Good. So any question from the floor? Welcome to put forward. Okay.
Oh, we have another one.
I found that cases, structure considerations as important construction considerations. As technology advances and the construction becomes easier and more precise, does that mean we can focus on more efficient structures rather than the more convenient constructions? So that's the relation between construction and the efficient structures.
Yes, thank you very much. This is also a great question. Let me start with the story. Bauersfeld, as I said, he was an optical engineer. In optical design, the dimensions are pretty different than the precision is also pretty different than what you use in construction. So I think the precision he prescribed for the dome with 40 meter span was 0.1 millimeter. So I would argue that was already a pretty precise construction with, as you could see from the images, maybe very low-tech solutions. So there is, I don't really think that there is a necessary correlation between how advanced tools you have and how precise you can construct. But this is just like a funny story. And the thing is that precision was actually super important because they figured out at one point during construction that there was some error. They rushed to the site and saw that there was a local buckling at one part of the dome. And they eventually figured out what was the problem. The problem was that not the right bar was put at the position, and the difference between the bar that was put there and what was supposed to be there was actually 1 millimeter, and that 1 millimeter difference resulted in a visible deformation of the shell. So I would definitely urge anyone who wants to design shells to be super precise. I'm not so sure that you would need a very advanced technology to achieve that. And I see where you are going with your question. So maybe if you have more advanced tools on the construction side, you can kind of relax conditions of how many elements you have. I think from a pragmatic point of view, you are completely right. So for example, if you have a robot to sort you the elements, you don't really have to worry about how many different you have, because you can make sure that you will always have the right one in your hand. But it was Frei Otto who said that whatever you can do in your head to make things more efficient, and by head you can safely think about the computer as well, you just have to do that. He was very much influenced by his own experiences when he tried to build things after, again, World War II with very little resources. So it was kind of a motto for him. But I still think for the greater good, you should optimize as much as possible before going to the work, to the construction site. And I do think it matters if there are fewer elements than more. But this is a personal view. I totally see that from a pragmatic point of view, it can be attacked.
Good. Interesting. Good. I have one question to Orsolya. I think your background, I'm quite interested in the education and BME because I think you have a very good research in the historical part of the structure. It's more like what's happening in the architect school in China and in the States. But at the same time, you have very deep research in the structural engineer. So could you introduce your background and how your education system constructed in your country? And at the same time, because you are now working in the form finding lab, we're also curious because SIGGRAPH made huge progress over the past few years. So also, could you introduce what's happening in the form finding lab right now? Yeah, maybe it's two questions about background introduction.
Okay, so I have mentioned that there was a very big influence on the educational system of Hungary from Germany. This was traditionally so because when the current university system of Hungary was established, which was at the end of the 19th century, many professors were sent to Germany to study, and they brought the way they thought about education back home from Germany. And I think part of that heritage is that at the Technical University of Budapest, which is my alma mater and where I also teach, we have a very solid curriculum also on the engineering side, which is complemented by a solid curriculum on the kind of architectural designer side. This is a constant kind of fight in one's mind. So the engineer versus the architect, it's like each and one of us is like already in a kind of cooperation with these two sides. So that's the reason we have relatively many subjects in structures. As I see here, for example, in the US, typically students have like 3 classes in structures, as opposed to our students still have at least 6, but some of them even more. So they have a solider background in classical structural mechanics. Mm-hmm. So that's that. And as you know from the introduction, I did my PhD in historical structures, which is essentially an engineering program. So that's why this interest in structures.
Mm-hmm. Great.
Yes, the form finding lab. I do think that they do amazing stuff here, but I'm also not SIGGRAPH. So I do not want to kind of speak on her behalf, but what I can and will kind of urge you to do is that on the website now there is a link to a recent exhibition that she had in Raleigh, where I was also lucky enough to contribute to the design of the exhibition. And it is a nice summary of all the work she has done in the past years. It's very well documented. It has texts, images, drawings, so you will have a very good insight. I will put the link into the chat window and you can check it out if that's okay.
Yes, please. That's fantastic. I think we're really interested in your topic. I think the history of shell structure in Hungary actually is the short history what's happening in Europe. I think it's quite relevance to what happening at the modern time in Europe. That is extremely interesting. Before the computational design happening, actually, this kind of shell structure based on the understanding of how to make a very efficient, optimal structure by both the geometry form finding and also by different algorithms. Actually, it's by hand, as you're introduced in your first part. I think it's extremely interesting. Because our background, the architects, maybe the algorithm part is a little bit difficult for us to understand in a very short time. But I think what's introduced about the tolerance and how to generate the geometry from the tessellation of different triangle and how to find different solutions to be the optimality of this kind of shell structure, extremely interesting. Right now, I think we have a lot of tools by computer can help us to generate different tessellation in design. But I think which is super interesting, how to understand why it's efficient and why it's an optimized solution. I think that's the knowledge part of the shell structure, which is super interesting from we can reading into the history. And we should maybe if more reading material, if you can send us, I would like to also send it to my students for them further research on this in this part. So thank you so much. At the same time, I'm right now the editor-in-chief of Architecture Intelligence, which is the journal, especially introduce not only the technology part of the building and structure engineer, but also we're interested in some historical part. So I think your first lecture is extremely interesting. If you would like to contribute some of your research, we will send you some email to introduce our journal, and also looking forward, you can contribute your research to us. I think.
Thank you very much.
In time to read in your paper to understand the details about your research, which is extremely deep, profound in the modern shell structure research. I think. And also we invite Pei Zhao, another professor who will come next time to introduce the South America modern shell architecture. I think that could be a very strong relevance to your lecture. So if you are interested in that, you're also welcome to come next week at the same time, because maybe you can have a very interesting talk on dialogue to each other. So thank you so much. Thank you so much.
Thank you very much. I would love to come next week. I'm super interested.
Thank you. And also please forward my regard to Sigrid. Say hello to her.
Definitely.
This year, I will go to make a keynote in IASS in Melbourne. So I don't know if you will coming to Melbourne this summer. So I think IASS this year.
Yes, I remember, and I would love to hear your thought. I would also love to go to Melbourne, but I think it's just not happening this year. But Sigrid will be there.
Okay, great.
And I will hope to catch you next year.
Okay, thank you. Okay, looking forward to that. Thank you so much for your lecture today.
Thank you very much for inviting me again. It was
I think it's already more. It's 10:15 in Shanghai at night. And good morning to you. Have a nice day. So let's keep in touch.
Yes, let's keep in touch.
Thank you so much.
All of you.
Bye-bye.
Thank you for listening. Bye.
Bye-bye. Thank you.
Thank you.